Good day to Doctor. We are from Group 12 and today we are going to present our group assignment, which is a problem-based learning assignment related to sand migration. I am Tan Jingxuan, who will be the first presenter in this video. Before I start my presentation, I would like to introduce my group members, which are 4 of us, me, LIEW, LIEW, and NURUL ATHIRAH. Now, let me start my presentation with an introduction to this assignment. This assignment is basically discussing the sand migration problem met by Mice Energy Sdn Bhd, which is an oil and gas company. So, what does sand migration actually mean? Sand migration refers to the movement of sand particles from unconsolidated formations into the wellbore and production equipment during oil and gas production. During the production, the flow of fluids in the reservoirs with unconsolidated formations can dislodge and carry sand particles along with it. Then, these sand particles can migrate from the reservoir into the wellbore. The sand and fine particles that remain in the wellbore can cause erosion of production facilities and equipment, leading to production downtime, costly repairs, and potential containment issues. With that, efficient sand control measures should be done to help maintain productivity, reduce equipment damage, and mitigate operational issues associated with sand production. Next, we will focus on the background of the problem. The main issue is the presence of the sand. Let us talk more about the sand. Sand particles have a granular structure consisting of individual grains that are typically angular or rounded in shape. The arrangement of these grains can vary, forming loose or compacted structures depending on factors such as grain size, moisture content, and compaction history. Sand particles can interlock with each other, creating a stable structure that allows for drainage and porosity. In general, sand particles have sizes ranging from 0.0625 mm to 2 mm, with medium-sized sand which is 0.125 to 0.25 mm being the most common. It is larger than colloidal particles as the size of colloidal particles ranges from 1 nanometer to 1 micrometer. The composition of sand particles can vary widely depending on the geological source. The most common mineral component of sand is silica, which is usually present in the form of quartz. Quartz sand is highly prevalent and has excellent chemical and physical stability. Other minerals found in sand can include feldspar, mica, garnet, olivine, and various rock fragments. In addition to minerals, sand particles can contain organic matter, shell fragments, and other biogenic materials depending on the source. For example, rich sands may contain shell fragments and coral debris. So, in order to remove the sand particles are needed to become negatively charged particles. There are 3 ways to form the negatively charged sand particles, which are specific ion adsorption, dissociation of surface functional groups, and substitution of surface ions. Specific ion adsorption can play a role in influencing the surface charge of the sand. When sand particles are in contact with an electrolyte solution that contains ions, ions from the solution can adsorb onto the surface of the sand particles. The adsorption process occurs due to the attractive forces between the charged surface sides on the sand particles and the ions in the solution. If the adsorbed ions are predominantly negatively charged, they can increase the negative charge on the sand surface, leading to form negatively charged sand particles. The second method is dissociation of surface functional groups. Sand particles are composed of minerals such as clay or silicates. Clay minerals in sand particles may have surface functional groups that can dissociate in aqueous solutions. These functional groups can release hydroxyl ions or other negatively charged species, leading to the negative charged sand particles. The last one will be the substitution of surface ions. As mentioned before, sand particles are composed of silicates which will have charge on the surface. When a solution containing ions comes into contact with the sand particles, the ions in the solution can bind to the charged surface sides through electrostatic interactions. For example, a silicon atom in clay may be replaced by aluminium, producing aluminium silicate with a surface of net negative charge.
Sand aggregation and sand agglomeration are processes in which individual sand particles come together to form larger agglomerates. Sand aggregation is the formation of granular loose sand particles. It is facilitated by forces such as van der Waals forces, hydrogen bonding, or electrostatic interactions. These forces result in the cohesive aggregation of sand particles, forming larger clusters. There are two destabilization mechanisms in sand aggregation, which are mechanical disruption and chemical dispersants. For mechanical disruption, aggregates can be mechanically disrupted by external forces such as water currents, wave action, or turbulence. These forces can break apart the bonds between sand particles, causing the aggregates to disintegrate and disperse. For chemical dispersants, the addition of chemical dispersants such as surfactants can disrupt the cohesive forces between sand particles. These dispersants reduce the interparticle attraction, leading to the dispersion of the sand aggregates into individual particles. Next is sand agglomeration. Sand agglomeration is the formation of larger, more tightly bound clusters or agglomerates of sand particles. It can occur naturally or be induced by external factors such as the presence of cementing agents, drying or heating processes. Agglomerates are often more resistant to dispersion compared to aggregates due to the stronger bonding between particles. Furthermore, the destabilization mechanisms in sand agglomeration are disintegration agents and the change in environmental conditions. For disintegration agents, chemical agents or mechanical processes can be used to disrupt the agglomerates and disintegrate them into individual sand particles. These agents can include water, surfactants, or physical agitation that weakens the bond between particles. The second one is the change in the environmental conditions. Altering the environmental conditions, such as temperature, humidity, or pH, can impact the stability of sand agglomerates. Changing in these conditions can weaken the bonds between particles and promote the dispersion of agglomerates.
To improve sand control, the use of chemical agent with aluminium sulfate to bond the sand grains together and create a solid matrix that reduces sand production. Alum is composed of aluminium cations Al3+, and sulfate anions SO4 2-. These ions are arranged in a crystal-lattice structure. The aluminium cations act as the bonding agents, while the sulfate anions surround and stabilize the structure. Now, let's talk about the destabilization mechanism, charge neutralization. In this process, the coagulant agent aluminium sulfate Al2SO43 or ferric chloride FeCl was added to the water containing suspended sand particles. The coagulant agent dissociates in water, releasing metal ions such as Al3+, aluminium cation, or Fe3+, ferric ion. These metal ions possess a positive charge and can attract negatively charged particles, including sand particles. The positively charged metal ions neutralize the negative charge on the surface of the sand particles, leading to reduced repulsive force between them. As a result, the destabilized sand particles come closer to each other, facilitating the formation of larger aggregates through subsequent processes like flocculation and sedimentation. These aggregates are then easier to remove from the water through physical separation methods, such as settling or filtration. Or we can say that when alum is dissolved in water, it forms aluminium hydroxide. This hydroxide reacts with the sand grains, causing the aluminium cations to bond with the surface of the sand particles. As more sand particles come into contact with the aluminium cations, they bond together, forming a solid matrix. This solid matrix provides mechanical stability, preventing the sand from being produced along with the oil. This helps to enhance the production efficiency and avoid equipment damage caused by sand erosion.
Suggestion for better performance of the coagulant agent. Use a combination of polymers instead of a single polymer system. By combining different polymers with complementary properties such as different charge densities or molecular weights, synergetic effect can be achieved. This can enhance the coagulation and the destabilization of particles, leading to improve the efficiency in removing suspended solids or contaminants from the water. The combine of polymer can provide enhanced flocculation, better particle bridging, and increased flux strength, resulting in improved water purification and sedimentation. There are few limitations of the destabilization method implemented. First, compatibility and the interaction, intimate dosage, cost and availability, complex performance and evaluation, and potential of environmental impact. In conclusion, it is crucial to conduct thoroughly the research, laboratory testing, and the feasibility studies to address this limitation and ensure the successful application of a combination of polymers as a coagulant agent. That's all from us. Thank you.